In recent years, there has been a wave of opposition to object-oriented programming in the programming community. Newer languages such as Go and Rust have chosen to abandon certain object-oriented features. This video will explain the problems with object-oriented programming and propose a solution to address its design flaws. First, let us discuss what programming paradigms actually do. Those who already understand programming paradigms may skip this section. Look at the two code snippets below. The one on the left is procedural, and the one on the right is object-oriented. Both code snippets convey the same meaning. First, perform the operation on F1, then F2, and then F3. The functionality is identical, only the expression differs. A programming paradigm refers to the way a program is expressed. Any program that can be written in object-oriented programming can also be written in procedural programming, and vice versa. If you are writing a shopping application, your application must include the functionality to buy items, regardless of the paradigm you use. Using a particular paradigm, procedural, object-oriented, or functional, does not mean your program lacks the ability to buy items. A programming paradigm is the way a program is expressed, but the way it is expressed does not determine what functionality you implement. It only affects whether you can express the functionality conveniently and understandably. In this example, procedural programming is actually the simplest. The code on the right, which forcibly uses object-oriented programming, makes the program more complex and harder to understand. Programming paradigms are designed to make code understandable to programmers. More specifically, their fundamental purpose is to facilitate large-scale code and collaborative teamwork. If your program is simple enough, procedural programming is perfectly fine. In fact, it's better for simplifying the program. However, when the code base expands to tens of thousands, hundreds of thousands, or even millions of lines, and the team has hundreds of programmers, the situation changes drastically. Enable teamwork. The entire project needs to be broken down into multiple modules, with each group responsible for one module. Programmers need to call modules developed by others. This requires module encapsulation and isolation. That is, encapsulating the module's operating principles within the module itself, exposing only the interface. The caller only needs to know how to operate the interface. They don't need to understand the module's internal workings to use it. If encapsulation and isolation are not done well, a problem arises. When calling other modules, you need a thorough understanding of their internal workings before you can call them. Since a project may have hundreds or thousands of modules, you would need to understand the internal workings of hundreds of modules to write your own code, which is impractical in real-world projects. The primary purpose of the current programming paradigm is to provide module encapsulation. Consider the following code. Object-oriented programming provides the class syntax, allowing programmers to easily break down the program into three parts: Class A, Class B, and Class C. Each class is a module, and each module contains several interfaces, functions that can be called externally. This example is simple, but in real-world projects, each of these three classes might have hundreds or thousands of lines of code, dozens of function interfaces, developed by different programmers, and used by yet another group of people. It's not that only object-oriented programming involves module encapsulation. Even if your programming language doesn't have the class syntax, you'll still need module encapsulation as your code grows. The method of expression doesn't determine the content being expressed. The programmer's job is module encapsulation. The specific programming paradigm used is irrelevant. Let's look at a procedural example. Each module is placed in a file and then imported. Package management is used for module encapsulation. The effect is the same as using classes. However, the problem is that this approach is too cumbersome and more complex than using classes. Engineering problems differ from mathematical problems. Mathematical algorithms don't need to consider cost. Engineering problems, on the other hand, prioritize cost. If the cost of using something outweighs the benefits, no one will use it, even if it's a good thing. We can call this the too expensive to use principle. High usage costs mean that only the most critical functions can adopt this approach. However, this solution is completely unsuitable for some minor, peripheral functions, as it would only complicate the program further. A programming paradigm should provide an expression that allows programmers to more easily do what they are already doing. Therefore, object-oriented programming is more advanced than procedural programming because it provides a convenient syntax for encapsulating interfaces. The names of classes and objects are truly misleading. When I was learning programming, teachers loved to use the analogy of a car with 4 wheels to explain classes and objects. Whether an object with a duck's head and wings is a duck type is truly misleading. The essence of a class is an interface. The quality of a class definition depends on whether it effectively encapsulates functionality and exposes the correct interface. Whether a car has many wheels or whether it's a duck is irrelevant. If an example is needed, a phone's power button should be used. The power button is an interface. Pressing it triggers a complex initialization process, which the user doesn't need to understand. They only need to know how to press the power button. At least in its initial design intent, object-oriented programming is more advanced than procedural programming. However, this isn't the case in practice. Because of design flaws, OOP cannot actually handle the task of module encapsulation. This is why the later languages Go and Rust abandoned some of their OOP design features. Let's discuss where the problems lie in OOP. OOP uses inheritance for code reuse. Consider this example. The main class inherits from class A inherits from B, and B inherits from C. This code splitting has a problem. The code for F1 and F2 cannot be reused. For example, if a user only needs F1 and F3, this code cannot be reused. Everyone has probably heard the saying composition over inheritance. The question is, what is composition? According to the composition principle, the code should look like this. Submodules are split into classes A, B, and C. The programmer writing the main class can choose which of F1, F2, and F3 to use, and leave the ones that are not needed and used. It's simple and flexible, far superior to single inheritance chains. Composition is a concept, not limited to a specific syntax. This concept is already understood. The building blocks we played with as children are an example of composition, breaking down the whole into its most individual parts and assembling them as needed. Multiple inheritance seems to support this code splitting, but in practice, it doesn't work. Inheritance cannot handle the complexities of real-world projects. Let's look at an example. This is an inheritance tree. Submodule A and submodule C have a function F1 with the same name, which will cause a conflict. Some might say, just rename one of the functions. However, real-world projects are not that simple. Modules A and C might be open-source libraries developed by 2 different companies, each potentially containing tens of thousands of lines of code. The call chain of function F1 could be extremely complex. Renaming it would require modifying the entire call chain. Furthermore, other libraries in the project might depend on the naming of these 2 libraries. Changing their names would require modifying those libraries as well. There might be more than one member variable or member function with the same name. The workload is staggering. But the real problem is that the original library might have been running in the industry for many years, with guaranteed security and stability. Modifying the source code carries the risk of introducing bugs. The key issue is that this requirement for modification is unreasonable. Let's compare it to examples from other fields. If a capacitor on a graphics card has the same name or model number as a capacitor on the motherboard, there won't be a naming conflict. In fact, the decomposition logic of industrial products is composition. The existence of parts with the same name in submodules doesn't affect anything at all. This is the correct encapsulation logic. Only OOP is so weird. In this situation, the inheritance syntax simply cannot handle it. Programmers can only look for other ways. A common way is MVC. In MVC, functionality is broken down into the finest model data and view functions, and then combined through the controller. Only the model or view function that is used is combined. Those that are not used are not combined. MVC is not like composition. MVC is composition. Instantiating 2 member variable objects in the main object, even if A and B have functions with the same name, will not cause a conflict. However, this controller approach has a problem: abstraction leakage. Let's look at a controller example. The main module has 2 submodules, A and B. When modules A and B have interaction logic, there are generally a few ways to write it. In the main module, A and B are initialized, and their pointers are swapped. Here's a problem. The initialization logic of A and B leaks into the main layer. In real projects, A and B might be underlying libraries written by other programmers, while the main module is written by the business layer programmer. The logic of the underlying libraries shouldn't leak into the business layer. Correct encapsulation means that each layer's programmer encapsulates its own logic within its own layer, and users shouldn't be required to understand layers' logic not belong to them. They only need to know how to use it. This example is simplified. In real projects, initialization can involve very complex interactions. For example, A might initialize several steps, pass the intermediate results to B for initialization, and then pass the intermediate results back to A to continue initialization. Furthermore, in real projects, there might be more than 2 submodules, and the initialization processes of multiple submodules might be intertwined. This requires the main programmer to have a thorough understanding of the internal implementation of submodules like A and B in order to write the main layer. Furthermore, abstraction leakage also leads to modules being unreplaceable. For example, library layer programmers cannot write a module C to replace module B because the main layer couples the initialization logic of module B. If module C's initialization logic is slightly different, it cannot replace B. Another approach is to add a middle layer, which can be written by programmers in layer A or B. Main layer programmers do not need to understand the internal implementation of the middle layer. This approach either lacks flexibility or results in extremely complex code. When writing code according to the example, the middle layer code is the simplest, but it lacks flexibility. Main layer programmers cannot choose to combine several submodules or combine other submodules with the same interface. For example, main cannot combine modules A, C, and D because the middle layer only implements the combination of A and B. If the middle layer is allowed to adapt to which submodules controller main can freely combine, the middle layer code will become extremely complex. Remember the principle of too expensive to use. There are 2 other solutions: dependency injection or microservices. These 2 solutions do indeed solve the problem of abstraction leakage. The quality of encapsulation can be measured by whether submodules can be replaced with similar modules. Both solutions allow for module replacement. The only problem is that these 2 solutions are too heavyweight. Remember the principle of too expensive to use. Only the most critical parts of the program will use these 2 solutions. Many smaller functionalities simply cannot use them. Returning to the first solution, let's analyze the root cause. There is a time paradox here. Modules A and B are written first, while the main module is written at some later point in time. To avoid abstraction leakage to the main layer, the programmer needs to express the swap pointers A and B before the main class appears. However, this is impossible because pointer names A and B only appear after the main class exists. But this is due to syntax limitations. If the compiler supports using abstract names as pointer names, the time paradox does not exist. Below is a syntax designed to solve this problem. The syntax largely follows inheritance, but when calling functions or member variables, the entire name chain of the member is used. 2 dots indicate searching upwards, 3 dots indicate searching to the same level, and 1 dot indicates searching downwards. Forward slashes, hyphens, and backslashes can also be used. The symbols are not important. The principle is, when the name chain is too long, the keyword use can be used for abbreviation. In essence, the use keyword is the same as include or import in traditional languages. The code uses the super keyword. Modules ABCD might be written first, while the main module might be written at some future point in time. Therefore, when writing ABCD, the programmer doesn't know the name of the future parent module. In this case, the super keyword can be used to represent a parent module with any name. With this syntax, the logic of lower-level modules is encapsulated at the lower level. The main programmer doesn't need to understand the lower-level modules. They only need to know how to compose them. Furthermore, similar modules can be arbitrarily replaced. For example, Module C has the same interface as Module B. The main programmer can arbitrarily combine B or C. If their names differ, they can be renamed using the keyword from. The keyword from and to is more important than it seems. It's essentially analogous to a motherboard designer connecting copper wires on a PCB. It's a cornerstone of this programming paradigm. Sometimes submodules might need the same class, in which case they can be renamed like main BB. However, in cases of abstraction leakage, it's impossible to freely replace submodules because the parent module is coupled to the lower-level implementation, and each lower-level implementation has different logic. Replacing a submodule would also require replacing the logic code leaking into the main layer. The core idea of this syntax is to mimic the production process of industrial products on an assembly line, where workers in different stages have functionally isolated roles. Workers in different stages don't need to understand the previous stage. They only need to assemble the parts transferred from the previous stage. Simultaneously, workers in one stage should provide packaged parts to workers in the next stage, so that the latter don't need to understand the logic of their own stage. Using the motherboard and graphics card example mentioned earlier, if a capacitor on the motherboard and a capacitor on the graphics card have the same name or model, there will be no name conflict because the motherboard and graphics card locate subcomponents through three-dimensional spatial positioning. The full-path routing in this syntax expresses the spatial positional relationship of object members, equivalent to a motherboard designer connecting copper wires on the PCB board according to spatial position. This syntax is equivalent to implementing dependency injection at compile time on the basis of object-oriented inheritance syntax. Therefore, this syntax is a development or improvement of object-oriented syntax, not a rejection of it. However, the basic syntax has a problem. The call chain is coupled with the name chain of other modules. Returning to the previous example, when module A calls module B, the call chain is coupled with the name chain from B to D. In real-world projects, module B might be an open-source library developed by another company, and its name chain might go from B to F and then to D. The programmer of module A cannot expect the programmer of module B to rename the code according to A's requirements. Therefore, this basic syntax only applies within a module where the programmer has complete control over the code. When modules interact, another encapsulation mechanism is needed, the API keyword. Consider this example. This syntax doesn't use the public and private keywords found in other object-oriented languages. Instead, it uses the API keyword to control visibility. When a module mod is not marked as API, all its member variables and member functions are public and can be called from outside, as can any external function. However, when a module is marked as an API mod, all members not marked as API become private and cannot be called from outside. Members marked as API can be accessed from outside. Furthermore, when an API mod accesses external resources, it can only call members of another API mod, not members of a regular mod. This logic is quite different from public and private. Does this seem difficult to understand? Actually, it's very easy to grasp. This logic is similar to the encapsulation logic of industrial products. Take the motherboard and graphics card example. Before installing a computer case, you can plug any hardware into the motherboard or directly modify the wires and capacitors. But when you put a case on the motherboard, the connection between the inside and outside of the case can only be achieved through interfaces on the case, such as USB or HDMI. The logic of disassembling and combining industrial products is the correct logic for modularization, abstraction, encapsulation, and interfaces. Let's look at a few more uses of the API keyword. B, C, and D are underlying modules written by others. Programmer A combines several submodules into a new module. Module A inherits from B, C, and D. The API keyword before B indicates that when inheriting from B, its API is also inherited. The absence of API before D means that when inheriting from D, its API is not inherited, but its implementation is. The keyword can make the implementation of F1 API of B into F3 of D. 2 is a very important concept. If you've ever seen PCB design software, this 2 is essentially equivalent to the action of connecting submodules. The API-only keyword indicates that when inheriting, only the API definition is inherited, but not all its implementations. The lazy keyword indicates that the submodule is not created along with the parent module. The programmer needs to create it manually. Designing syntax isn't about designing syntax itself, but about designing program architecture and development processes. Programmers first envision an architecture, then design the syntax. The syntax is simply a means to more easily implement that architecture. Using the syntax described in this video, you can write programs that resemble a logical architecture. I call this the architecture-oriented programming paradigm. The code itself is the architecture. The code itself is its own module architecture diagram. When programmers give presentations and explain a project's design architecture, they use a module architecture diagram as an example. This is because module diagrams, or logical architecture diagrams, are the most suitable language for human understanding, easier to comprehend than natural human language. Even infants can understand images before they understand human language. Imagine if you didn't use module diagrams and only used natural human language to explain the project architecture to an audience. The audience would find it much harder to understand. If a program's logical architecture diagram is as shown on the left, then using this syntax, a programmer can write the program as shown in the middle. You can see that the code and the logical architecture are completely consistent, a one-to-one correspondence. In traditional object-oriented languages, code might look like the one on the right. Although the logical architecture of the code on the right is the same as the one on the left, it looks different because the logical architecture information is scattered in 3 places: inheritance, controller, and package management, making it difficult to understand at a glance. Clearly, programs expressed using the syntax described in this video are the easiest to understand and the easiest to write. When programmers design programs, they always first conceive of the logical architecture in their minds. Using this paradigm, programmers can directly write down the architecture in their minds. In the object-oriented paradigm, however, programmers need to perform a mental transformation, translating it into the architecture shown on the right, which is a mental burden. When others read this code, they also need to analyze the logical architecture. So why not write the program in the form of a logical architecture from the beginning, making it both easy to read and easy to write, convenient for both the reader and the writer? Using this paradigm, the code expresses the program architecture. The name, architecture-oriented programming, is actually redundant. Other design fields, such as 3D modeling and PCB circuit design, have never distinguished between procedural, object-oriented, and structure-oriented because designers designed the architecture. There's no need to add unnecessary embellishments. If the programming paradigm is designed correctly, the concept of a programming paradigm becomes unnecessary. Functions, interfaces, and modules are simply different structure types. The appropriate structure is used based on the usage scenario. If a structure is needed, it's used, and if not, it's not. Programmers shouldn't limit themselves to structures like pure functions or objects. Using this programming paradigm, the development process might look like this. The architect uses graphical software to draw a module architecture diagram and defines the interfaces of each module. A code framework can be generated based on the diagram, as shown in the middle. Finally, the programmer fills in the code, as shown in the right image. Alternatively, the programmer can write the code and use tools to extract the inheritance tree from the code, automatically generating the module architecture diagram. Because there's a one-to-one correspondence between the code and the module diagram, seamless conversion is possible. This brings 2 seemingly obsolete technologies back to the forefront: UML, ADL, and visual programming. UML stands for Unified Modeling Language, and ADL, short for Architecture Description Language, is similar. Both are languages for describing program architecture. UML is now largely unused, but if you compare them, you'll find that the syntax described in this video is similar to UML. The programming language itself has become its own UML. The reason UML didn't become popular is that it's inconsistent with project code. Using it in a project requires maintaining 2 sets of code. Remember the too expensive to use principle? If it's too cumbersome to use, even if it's good, nobody will use it. Similarly, visual programming has been popular for the past 20 years. Imagine dragging a few blocks onto a board, connecting them, and the program is done. It sounded great, but now almost all programmers agree that it's impossible. The reason visual programming was previously unusable was due to abstraction leakage. When users assemble 2 submodules, they always have to write the leaked program logic. The problem is, users of visual programming use it precisely because they can't understand the code. Why would you ask me to write the leaked logic code? Isn't that putting the cart before the horse? This syntax solves the problem of abstraction leakage. Writing programs will be similar to PCB design software. Just drag and drop several submodules and connect them. There's no reason why a method that works in computer hardware design can't be used in software design, because hardware and software are inherently integrated, simply different layers of abstraction on a single line. The keyword "to" in this syntax is equivalent to connecting different submodules in PCB design software. This syntax is helpful for AI programming. Some might think that in the future, AI will automatically generate code, and abstraction leaks will be tolerated since it's all AI written and humans don't need to worry. Those who think this way have clearly never written code with AI. Even if AI could perfectly understand human requirements, it wouldn't matter, let alone its ability to comprehend them perfectly. For example, if you tell AI to write an FPS shooting game, how does AI know if you want a fast-paced or slow-paced game? You have to tell AI you want a fast-paced one. And how does AI know how many weapons you want? Perhaps the AI created 10 weapons, while you want 20. Therefore, collaborative programming between humans and AI requires constant communication of requirements with the AI, gradually bringing the program closer to the desired result. It's impossible for AI to write a perfectly compliant program in one go, because the operator cannot clearly describe it all at once. Continuous communication and iteration are necessary. This is the same as purely human project development, which also requires constant communication of requirements. However, in the future, human programmers will primarily act as architects, designing the architecture, letting AI handle the specific implementation, and then the programmers will glue the AI-generated modules into the project, constantly having the AI adjust certain modules. If the code contains abstraction leaks, you won't be able to integrate the AI-generated code into your project because you'll have to deal with the leaked parts. The problem is, you can't possibly understand the internal logic of all the underlying modules. That's impossible in practice. Another issue with AI code modification is its tendency to modify other areas of code indiscriminately. If you tell the AI to modify one weapon, it might end up modifying the logic of another weapon as well. To solve this, you need to tell the AI to only modify that specific module, limiting its modifications to other areas and confining its changes to a specific region. The more you collaborate with AI, the more crucial it is to provide abstract isolation in the syntax to avoid code leaks. Because this syntax's inheritance tree has complete code relationships, future code can be decoupled from the file system. The code no longer resides in the file system, but is stored in a special code database, which facilitates the development of programming tools. C++ and Java recommend storing only one class's code per file. This approach has been almost entirely phased out in later languages like Python, Go, and Rust. In fact, they all aim to simplify ineffective scopes. Files, classes, and functions all express scoped. If you've noticed the use keyword in this syntax, it's essentially the same as import and include in package management. Anything packaged will have a corresponding instance under mod. Classes, files, and packages can be compiled into the same thing because they are essentially the same thing. Scope. In C++, a file scope contains only one class scope, thus unifying the class scope and file scope into one. You can directly treat the tree structure of the file directory as the logical architecture tree of the program, which is ideal but poorly implemented. Due to abstraction leakage, this solution cannot actually decouple the file system. In C++, if you have 10 classes, each in a separate file, you'll have 10 class scopes and 10 file scopes, a total of 20 scopes to manage. 10 of these file scopes don't express any meaning. They're invalid information, yet they waste the programmer's time and energy managing them. Therefore, Python abandoned this approach. Multiple classes can be stored in a single file, so 10 classes in one file would result in 11 scopes, 9 fewer than C++. Go goes further, eliminating classes altogether. All code resides in a single file, requiring only one scope for management, further reducing the programmer's burden. The syntax described in this video, however, retains the class scope but removes the file scope. 10 classes, not stored in any files, would only have 10 scopes. If you replace the directory structure on the left side of your IDE with the inheritance tree from this syntax, displaying the class code on the right, and compare it to C++'s one file one class convention, you'll find that this is actually what C++ intended. This outdated code arrangement in C++ was actually correct, but the lack of a crucial syntactic feature made it too cumbersome, leading to its elimination. Remember, too expensive to use. This is why this video strongly emphasizes this principle. Many outdated designs, in the long run, are actually the correct path. As mentioned above, both files and classes are scopes, so from this perspective, deleting class scopes is equivalent to deleting file scopes. That is, this syntax decouples the file system, which is equivalent to putting Go code in a single file. However, Go's approach is flawed. If programming languages don't evolve and no new features are added in the future, then Go's approach of deleting class scopes and keeping file scopes is correct. But future programming languages will inevitably evolve, and new features will certainly mark the logical structure of code. The syntax in this video, which unifies the logical structure of code within the inheritance tree, will greatly facilitate new syntax features that mark structures. This would be very cumbersome in Go's design of deleting class scopes and keeping file scopes. I have a manual memory management design, explained in another video, from which you can see the difference between the two approaches. This memory management method only works well under this syntax. Theoretically, it can also be implemented in object-oriented programming because object-oriented programming also has a logical architecture tree, but it would be very inefficient. This is because the object-oriented architecture tree is scattered across package management, inheritance, and controllers. What one marker can do becomes 3 markers in object-oriented programming, making it very inconvenient.